Hello everybody! Today I want to talk about my attempts to make logic gates based on optical interference. So optical interference is probably best known from when you place two semi-reflective surfaces close to each other and you observe these bright and dark fringes under monochromatic lighting conditions. And these fringes are caused by variations in the distance between the two surfaces, resulting in areas of constructive and destructive interference of light. Now, a common explanation given for destructive interference is that the light reflected off the two surfaces is sort of out of phase and the electromagnetic waves sort of cancel each other out. But in terms of conservation of energy, this explanation does not make sense at all. Because where would the electromagnetic energy contained in the dark fringes go to? So, in my opinion, the term destructive interference is kind of misleading, even though I myself use it all the time, for lack of a better word. But it suggests that the electromagnetic radiation is somehow destroyed, and that is definitely not the case. So where does the energy go when we observe destructive interference? Well, the answer is simple. It's going somewhere else. For example, in the case of the semi-reflective surfaces, more light is transmitted in the areas that display destructive interference in reflection. And in a more general sense, we can state that electromagnetic radiation such as light cannot just disappear between its emission and absorption. I mean, a lot can happen in between. The radiation can be reflected, refracted, diffracted, but as long as it's not absorbed, the total amount of energy in the electromagnetic wave remains unaltered. And whereas the processes involved in emission and absorption always involve quantization, the transportation mechanism for the energy between these two events always behaves as a pure and elastic wave, without any noticeable quantization in space or time. Anyway, this is not the path I want to go down on, at least not today, because in this video I want to discuss something of a more practical nature, which is a way to make logic devices based on optical interference. But let us first take a look at what logic devices, also called logic gates, are exactly. Logic gates find widespread application in modern electronics as all sort of logical switches. And here's an overview of some very common logic gates. And they all have in common that you send logic values like true or false to the inputs, assigned here as A and B in this figure. So true is shown as a 1 and false as a 0. And the gate consists of some hardware that takes these input values and then performs a logic operation on them and sends the result to an output. Each type of logic gate handles the input values in a somewhat different way. Let's say we have a gate with two inputs, and with the two different states for each input, this means that there are a total of 4 distinct input states possible. So let's take, for example, the OR operation. The only state where the OR gate results in the output of a 0 is when both inputs are 0. But if either of the inputs has the value 1, or both, the output will be 1. Now, logic gates used in electronics use voltage levels to represent the 0 and the 1, which are either higher or lower than a specific threshold value. And in the case of optical logic, we can imagine something similar, where the light intensity at the inputs or at the output are a measure for the logic value. A purely optical OR gate would actually not be very difficult to construct. Basically, we would just lead the light of both inputs to the output and then determine if the light level at the output is above a specific threshold value. And if it is, then the output is considered a 1, otherwise it would be a 0. However, this is only true if there is no destructive interference, because in that case we would get a 0 value result if both inputs are on. So if we look up what kind of logic gate this represents in the overview, we arrive at the exclusive OR gate. And similarly, we could come up with a gate that exploits local constructive interference and only outputs the value 1 if both inputs are on. And this configuration would be an AND gate. Now, the idea of using optical interference to perform logic operations has been on my mind for quite some time. And of course, I did what almost everyone does when they have an idea. I quickly searched the internet to see if someone had already done this. And guess what? People did. but actually not in the way that I had imagined. So I quickly stopped looking because I did not want to get too distracted from the original idea. But if you know of people who have done exactly the same thing, please leave a comment. Let's go right to the core of the concept that I had in mind. As a light source, I wanted to use a coherent monochromatic beam such as the one produced by a diode laser, and the beam is divided into two paths, A and B, which can be switched on and off individually. So later in this video I will get back to how to switch the beams, but let's for now focus on the logic operation performed by the light. And this is done by using two optically active planes, and for reference I've named them the generator and the evaluator. The generator plane contains the actual diffractive elements and generates an interferometric pattern. And the optical interference pattern is then evaluated in the second plane, which basically acts as a simple filter and produces the logic output value. Let's have a look at how this could work in practice. Say the two diffractive elements that serve as the signal inputs both direct the light to a common focal point. In the case that the light from both elements arrives in phase at the focal point, we will have constructive interference. So if we place a pinhole in the evaluation plane at the focal point, there will be light passing through the pinhole for three different input states. And only if both inputs receive no light at all, we will have no light at the output, or in other words, a zero value result. So the current configuration represents a very simple OR gate. But if we use the same configuration and shift one of the beams 180 degrees out of phase with respect to the other beam, we will create a different kind of logic gate. In that case, light will be passing the evaluator when only one of the gate inputs is on, because if both inputs are on, interference results in a zero intensity exactly in the center of the common focal point. And if we look at what kind of logic scheme this situation represents, it is equivalent to the exclusive OR gate. Let's do another example. We could add an additional light path that is always on, so it's actually not part of the logic evaluation. And if we make this particular input such that it is out of phase with the two switchable inputs, we can easily create an exclusive NOR gate. So I guess by now you will probably get the general idea. And by clever use of the principles of interference, it should be possible to design every single type of logic gate shown in the overview. Now, having an idea is one thing, but in reality, things are always different and more complicated than they are in your head. So the next step was making and testing some diffractive patterns. And in previous videos, I've shown how I do this, which is by using photolithography as a manufacturing method and a home-built digital wafer stepper as the main tool. I will not repeat myself here, but I will just post links in the description for reference. Now for this experiment, the diffractive patterns were etched in a thin, non-transparent chromium layer on top of a quartz carrier. And with this process you can create these microscopic transparent areas in the chromium which have diffractive properties due to their shape and size. And they have to be really tiny because you can only effectively diffract light with features that are of the same order of magnitude in size as the wavelength of light. Because the patterns are so very small, we need a microscope to study the development of the optical wavefront behind them. And for this I also used a method which was demonstrated in previous videos. Basically I used a property that most microscopes have, which is a very shallow depth of focus. And this allows you to observe the light intensity distribution present in the focal plane of the microscope. And to avoid confusion, the focal plane of the microscope will be referred to as the observation plane in the rest of this video. Let me just show you what it looks like when you move the observation plane through a beam of light that has been diffracted by a pattern. Here we have such a diffractive pattern in focus under the microscope, and the pattern has a diameter of about 150 microns. So this makes the smallest features in the pattern only a few microns wide. Now the observation plane is now leveled with the pattern etched in the chromium, so in focus, and you see the light of the laser seeping through the transparent parts of the pattern. As we move the observation plane away from the diffractive pattern, we observe how the wavefront of the light is concentrated towards a focal point, which in this case is next to the area of the diffractive pattern. So let's make this type of pattern the first input of the logic device and create a second input which is identical and at exactly the same distance from the focal point. If we look at the common focal point, we see that this results in nice constructive interference with the highest intensity right at the center of the original focal point. But also notice these dark bands. Apparently inside the common focal point we have created areas of destructive interference. But if we were to add an evaluator plane at this distance from the diffractive elements and create an aperture right at the center of the common focal point, we would have produced an optical OR gate. Here I have replaced one of the input patterns with another one that has an identical focal distance but that shifts the light 180 degrees out of phase. By the way, this is done simply by inverting the diffractive pattern. So to see what is happening, we need to zoom in on the focal point in a little more detail. And as you can see now, the two parts of the pattern create a dark line right in the center of the overlapping focal points. So now if we were to use a slit-shaped aperture in the evaluator plane, the output would be in the off state with both inputs on. However, if only one of the inputs is illuminated, the result at the output will be the on state, because this same aperture will be in the center for each of the two individual focal points. So by just inverting the phase of one of the inputs, we've just easily converted an OR gate to an exclusive OR gate. Now I must admit that I would have wanted the effects and especially the areas of interference a bit larger. But I guess the main reason for the areas to be so narrow is the large angle under which the light is refracted by the inputs. So there's definitely room for improvement here. One of the things that I found while playing around with different patterns is that indeed light always shows up somewhere else if you create areas of destructive interference. Now, during my futile quest to make a completely focal pointless lens, I designed a handful of Fresnel zone plates. And as you can see, half of the lens surface diffracts the light out of phase with respect to the other half of the surface. Only to find out that instead of a single focal point, I had just created a lens with 2, 4 or even 8 new focal points in return. Even this attempt, which I briefly considered a demonstration of pure genius, turned out to be another hopeless attempt. So here the out-of-phase elements are both centered exactly around the common focal point. But even this attempt resulted in 2 focal points, this time not next to each other, like with the previous patterns, but now on top of each other. And they can be observed when I move the observation plane through the focal point of the diffraction pattern. First we observe a focal point right here, closer to the lens surface than normal. And then we observe a ring with destructive interference in the center. And when I move the observation plane further away from the lens, we observe a second focal point, right on top of the other one. So far I have not made full logic devices, and this video was basically intended just to demonstrate the principle and maybe get some feedback or ideas from you viewers before I attempt to do this. Also, I need my thermal evaporator to be up and running to deposit the evaluator layer. And sure, I think one could come up with way more effective diffractive patterns. So what about applications? Well, imagine creating a plate that contains several millions of these logical elements, which is sandwiched between a small transmissive LCD screen and a CCD sensor. Now the LCD would switch the inputs and the CCD sensor would read out the results. And this configuration can in principle perform millions of logical operations in parallel. And by the way, they are not limited to simple true or false logic evaluations. They could also involve complex analog calculus. But whether this could compete with computer chips in speed and versatility is of course very much the question. I guess it would be dependent on a specific application. Another and much more down-to-earth application would be to use the logic to make a truly unpickable optical lock. And that will put even the best lockpicking criminal or lawyer out of business for good. So I hope you found this interesting. And if you did, please subscribe to the channel, because I'm definitely going to return to this subject in the future.